we'll hit some new material. So we ended up, last time we talked about ratios and proportions and how that kind of is the basis for many of the things we do in math. It's actually going to be one of the biggest concepts as far as our dosage calculations in the next unit. Today I want to make sure we go over some of the other basics we need. The chemistry part of it is huge if you go into any medical field as far as the anatomy and physiology. So these are going to be skills that would be huge dealing with the chemistry side of things. Oops, we just lost Prentice. Prentice, are you guys still there? Okay, well, hopefully they come back online here soon. So anyway, for those of you that were not here on Monday, the assignment that we looked at in the book was page 73, 1 through 39, the odd. Then on page 78, just a review of percents, 1 through 35, the odd. So if you do those and have any other questions, we'll take time on Friday to answer those for you as well, since some of you guys had President's Day off. Okay, so now, new material for today, we're going to be looking at things that look like this. Of course, that means 8 to the third power, and it represents, of course, 3 8s being multiplied together, or 512. Now for that one, 8 to the third, or 8 times 8 times 8, it wouldn't be so bad if you had to punch that in the calculator as repeated multiplication like that. But if we have something like 2 to the power of 11, we don't want to be punching that in, as 2 times 2 times 2 times 2. So most of you, I'm sure, know about this button. For most calculators, it's a button that looks like that. It is called the caret key. And that is the power key. Some of your other calculators might have an X to the Y key or Y to the X key or something similar. There might just be empty boxes on there to simulate it. Any of those buttons work exactly the same way. It's 2, you press that button, and then put in your power of 11, should come out to 2048. Well, we're not so concerned about actually calculating those amounts today, because I know you guys can do that with the calculator. What we want to look for is the rules with those patterns. And I know you guys have seen these rules with the powers, but I want to make sure we have them down, because the next step, it's important that we be able to work with those powers. So now what we're dealing with here is an exponent, 8 to the third. And an exponent has 2 parts to it. There is the base. The base is the number that we're starting with, the number that is being taken to that power. And then there is, of course, the power. And that is the part that many people think of as the exponent, but the exponent really is both numbers with the 2 parts. So when I say that 2 exponents have the same base, what I'm meaning is that bottom number is the same. So if I have something like x to the third and x to the fifth, those are exponents that have the same base. And we're going to be looking at combining exponents with the same base. And we've already done this. This is going to be 3 plus 5, or 8. So it's x to the 8th. We keep that same base. If you recall, for division, x to the 7th divided by x to the 3rd produced x to the 4th. We subtracted the powers when we divided. Again, if we had exponents with the same base, when we're dividing, we subtract the powers. And we had x to the 4th to another power, maybe the power of the 11th. Here, when we have an exponent that's being taken to another power, we multiply the powers. 4 times 11 was 44. Now, some things that we need to figure out with these powers. What is x to the power of 0? Well, just like when we were talking about negatives, we looked at patterns. Here's another spot where our basic definition of a power breaks down. I mean, x to the power of 0 means you have 0 x's being multiplied together. That doesn't make any sense. So to figure out what it means to be a power of 0, we're going to look for a pattern. So we're going to actually look at powers of 10. So let's start out with 10 to the power of 4. Of course, 10 times 10 times 10 times 10 comes out to be 10,000. Now, many of you probably learned a shortcut for powers of 10. That's 10 to the power of 4. That means there's 4 zeros there. 10 to the power of 3 then, 10 times 10 times 10 is 1,000. 10 to the power of 2 is 100. So now let's look to see if there's a pattern here. So we're starting with exponents that all have a base of 10. And we're reducing the power by 1 each time. We went from 4 down to 3, then from 3 down to 2. What happens to our result? Well, we went from 10,000 down to 1,000. It was divided by 10. From 1,000 down to 100, it was divided by 10. So if we keep going with our pattern here, reducing that power by another one, 10 to the 1, well, that's just a single 10, so that's 10. And we can see the pattern continues. We reduce the power by 1, the result was divided by 10. So if we keep going, reducing the power by 1 would be 10 to the 0. We'd have to divide by 10 again. 10 divided by 10 is 1. And we could do a pattern like this for any base that we wanted to put out there. We could do 8 to the power of 0, or 7 to the power of 0, or any number, even a variable that we want to put in there. What we find is anything to the power of 0 equals 1. Now, I won't do it to you in this class, but if you're in some of my technical math classes or something like that, I might do something to you just to see if you're paying attention. It looks like this. Of course, that's going to equal 1 because it's to the power of 0. So you don't have to figure out all that mess inside there. It's all to the power of 0, so it equals 1. Now we can keep going with this and define negative powers. 10 to the power of negative 1. Well, you divide by 10 again. 1 divided by 10 is 1/10. 10 to the power of negative 2 dividing by 10 again is 1/100th. 10 to the negative 3 dividing by 10 again would be 1 over 1,000. And what we find is there's a relationship between the negative powers and the positive powers. 10 to the power of negative 3 is the reciprocal of 10 to the positive 3. 1 over 1,000, of course, is the reciprocal of 1,000. So if we have 10 to the negative 8, that's just 1 over 10 to the power of 8, or 1 over 100 million. So now these powers of 10, if you looked at what we had for our list over here, they should look very familiar to us because that's what we used for our place values. Oops, don't need to cross my L. Remember our place values, if we started at the decimal point, we can say that this first place value here is 10 to the 0, or the ones place, 10 to the 1, or the tens place, 10 squared, or the hundreds place, 10 to the third are the 1,000s, 10 to the fourth, the 10,000s, and going up the line. And going the other way, we've seen that this is 10 to the negative 1, or 1/10, 10 to the negative 2, or 1/100th, 10 to the negative 3, or 1/1000th, and going down that direction. Now, we often try to abbreviate numbers. We might have something like 3,700,000. And one of the ways we abbreviate that number is just by pronouncing it as 3.7 million. Rather than saying the word million there, we could actually abbreviate it by using its place value as a power of 10. 3.7 times 10 to the power of 6, or 10 to the 6th. So as you probably have guessed by now, that is where our scientific notation comes from. We are abbreviating our numbers by naming the first digit. So we take our first digit and put that in front of the decimal point, and then we name its place value. So if I have something like 0.00082, I look for that first non-zero digit, which is the 8. I'm going to put the decimal point after that, so it becomes 8.2, and the place value of that 8 is in the 10 to the negative 4's place. Likewise, I could have 45,000. Again, I look at the first non-zero digit is the 4, so I'm going to put the decimal point after the 4, 4.5, and that 4 is in the 10 to the 4th place, so times 10 to the 4th. Now, we don't want to have to draw out our place values every time we convert numbers into scientific notation. So let's look to see if there are some shortcuts, some patterns we can find. First of all, large numbers, in other words, numbers that are larger than 1, all have place values that are positive powers of 10. So the positive power of 10 place values are our large numbers. Numbers that are smaller than 1, our decimal numbers, all have place values that are in the negative powers of 10. So any of these numbers that have their first non-zero digit after the decimal point would be less than 1. Those are in the negative powers of 10. The second thing, and this is probably how you were taught to do scientific notation, for our 3.7 million or 3,700,000, the decimal point starts right here, and we want to put it here after that first non-zero digit, after the 3. It has to move 1, 2, 3, 4, 5, 6 places. So it became 3.7 times 10 to the 6th. That power of 10 describes how many places we had to move the decimal point. So let's take a look at some examples without having the place values in front of us. So 0.00509, or 509 hundred-thousandths. Our first non-zero digit is the 5, so the focus is on the 5. We put our decimal point after the 5, so 5.09, and we name the place value. Well, that would have been, the decimal point has to go 1, 2, 3 spots, so it's going to be 10 to, it's going to be 3 in the power. But this number is smaller than 1, so that is in the negative power of 10 place values. So that's 5.09 times 10 to the negative 3. 470 million. Again, the first non-zero digit is our 4. That's where we're going to focus. That's going to be 4.7 times 10 to the, well, our decimal point started here, moves to there. It went 1, 2, 3, 4, 5, 6, 7, 8 places. So 10 to the 8th. That's a large number, much bigger than 1, so that's a positive power of 10. So 10 to the positive 8th. And of course, we can go the other direction. If I have 7.1 times 10 to the 7th, I'm going to take that 7.1 and move my decimal point. Now this is 10 to the positive 7th. So since that's positive, this number is going to be a large number. So we're making the number larger. So we move our decimal point over to make it larger. We go one place, but it's a power of 7. We have to go 7 places. So we're going to have to add zeros. So there's 1, 2, add another 0, 3, 4, 5, 6, and 7. So that is 7.1 times 10 to the 7th is 71 million. So my pen's acting up today. There we go. Or we might have 2.8 times 10 to the negative 5. So again, we start with that 2.8. And the negative 5 means our decimal point has to move 5 spots. It's negative, so that means it's a small number. So we're moving it 5 spots to make this smaller. Move 1 spot, and then we start adding zeros again. That's 2, add another 0, 3, 4, and 5. So that's where my decimal point goes. So that is 0.123428, or 28 millionths. Where a lot of people get confused is if negatives get put on these numbers. If I have negative 380,000 and I want to convert that into scientific notation, so my negative on there. The negative doesn't affect the way I do the rest of it. My first non-zero digit here is still the 3. So I'm going to focus on that 3. The decimal point is going to go after it. So that becomes 3.8. Decimal point still had to go 1, 2, 3, 4, 5 spots. So that's 10 to the 5th. Now I'm ignoring the negative at this point. 380,000 is a large number, so that tells me that has to be a positive 5. Now we deal with the negative, and that simply goes on front. The 3.8 is negative. It does not affect the power on the 10 at all. Likewise, something like this. So our first non-zero digit is the 7. So 7.08, our decimal point is going to go right there. The decimal point had to go 1, 2, 3, 4, 5, 6 spots. So that's 10 to the negative 6. The negative just goes back on front, making that a negative 7.08. So we can convert numbers from standard notation into scientific notation. Let's take a look at operations. Now remember, we flash back when we add or subtract. I know you're probably sick of hearing these rules by now, but they're very important throughout all of math. The first thing is we need the same name. And then, of course, we're going to combine the counts. We always combine the counts no matter what operation we're doing. And we keep the same name. So those are the important things for adding and subtracting. So if I look at a number in scientific notation, 3.8 times 10 to the 7th. When we were doing our whole numbers, remember we said the name actually was hidden within the number as the place value of each digit. Well, in scientific notation, the part that represents the place value is right here, the power of 10. That is the name of a number in scientific notation. This number is 10 to the 7th. When I add or subtract, I have to have the same name. So for scientific notation, that means I have to have the same power of 10. So we might have 3.8 times 10 to the 7th. Now I'm putting that in parentheses not because I need to do anything there first. The parentheses are just separating that like they would a negative number. Plus 2.5 times 10 to the 7th. These both have the same name. Both are 10 to the 7th. So I can go ahead and combine them with addition. When I add, we combine the counts. So 3.8 plus 2.5 is 6.3. And then I keep the same name. So I keep the times 10 to the 7th. Doesn't always stay quite that simple. We can end up with things like 8.6 times 10 to the 12th plus 5.2 times 10 to the 12th. We have the same name. They're both 10 to the 12th. So we're going to combine the counts. 8.6 plus 5.2 is 13.8. And we keep that same name, times 10 to the 12th. Now there's a small issue here because this is not proper scientific notation. Proper scientific notation, we only have one digit in front of the decimal point. So we have to move that decimal point over to make that 1.38. Now we move the decimal point, our power of 10 has to change. This number here went from 13 to 1. It got smaller by one decimal place. So our power of 10 has to get larger by 1. 12 plus 1 is 13. So one decimal place equals one power of 10. It can be a little bit trickier if we have negative powers of 10. If we have something like 7.2 times 10 to the negative 8th plus 9.4 times 10 to the negative 8th. Now we have the same power of 10, so again we can just combine the counts. 7.2 plus 9.4 is 16.6, and we keep that same name of 10 to the negative 8th. Now once again, there's more than one digit in front of the decimal point here, so we're going to have to move that over. So that's going to give us 1.66. Now that number got smaller again. That means our power of 10 has to get larger. Negative 8 plus 1 is negative 7. Be careful. A lot of people will try to put negative 9 on there. But when the negative numbers, adding 1, we're getting closer to 0. So what if we don't have the same power of 10? What if we have 6.43 times 10 to the 9th plus 9.2 times 10 to the 8th? Well, generally, what we have to do is we have to give them both the same power of 10. Generally, what we will do is we will go to the larger power of 10. In this case, that's the 10 to the 9th. So that 6.43 times 10 to the 9th is not going to change. Over here, however, we're changing 10 to the 8th to 10 to the 9th. Now, this is just going to be the opposite of what we did up here to our solutions. Now the power of 10 is getting larger, so the number over here has to get smaller. Power of 10 got larger by 1. This has to get smaller by 1 decimal place. 0.92 times 10 to the 9th. So now we can combine our counts. 6.43 plus 0.92, 7.35, and we keep that same name. So times 10 to the 9th. Subtraction works pretty much the same way. We might have 7.6 times 10 to the 12th minus 5.9 times 10 to the 12th. Again, we have the same power of 10, so we have the same name. So we go to combine the counts. 7.6 minus 5.9, because we're subtracting now, is 1.6. And we still keep the same name, 10 to the 12th. We can run into issues here, of course. We might have 8.53 times 10 to the 9th minus 7.89 times 10 to the 9th. We go to subtract here, 8.53 minus 7.89 is 0.64. Then we keep our same name of 10 to the 9th. Now here again we have an issue. There isn't a number in front of the decimal point except for the 0. We have to have, for proper scientific notation, we have to have one non-zero number in front of the decimal point. So we have to move that decimal point the other direction this time. So 0.64 becomes 6.4. Now this time, this number got larger by one place value. So our power of 10 has to get smaller by 1. So 9 minus 1 is 8, so that's 10 to the 8th. If we have negative powers of 10, we might have 6.42 times 10 to the negative 11th minus 5.91 times 10 to the negative 11th. Again, we have the same power of 10, so we can just go ahead and proceed. 6.42 minus 5.91 is 0.51. We keep the same name, so times 10 to the negative 11th. Well, once again, there's an issue here. This has no non-zero numbers in front of the decimal point, so we have to move that decimal point. So that's going to become 5.1. This number got larger, so the power of 10 has to get smaller. It got larger by one place value. The power of 10 gets smaller by 1. So negative 11 minus 1 is negative 12. So you get 5.1 times 10 to the negative 12. So when we multiply, remember, when we multiply or divide, we do not need the same name. And obviously we combine counts, as always, but we also combine the names. So what that means is I can take something that looks like this, 5.2 times 10 to the 9th, and I can multiply it by 1.3 times 10 to the 15th. It does not matter that they have different names, because when we multiply, we're also going to combine the names. So we're going to multiply the counts. 5.2 times 1.3. Oops, let's clear that out. Let's try that again. 5.2 times 1.3 gives us 6.76. But now for our power of 10, we're also going to combine the names. So we have 10 to the 9th times 10 to the 15th. So those are exponents with the same base. They both have a base of 10. So we're going to, when we multiply them, we add the powers. 9 plus 15 is 24. That's 6.7 times 10 to the 24th. Just like with addition, we can run into issues like this. 7.3 times 10 to the negative 12th times 5.6 times 10 to the 8th. Again, notice the powers of 10 are not the same because we can multiply things with different names. So we'll start out combining the count. 7.3 times 5.6. 40.88. Then we also combine the names. 10 to the 12th or 10 to the negative 12th times 10 to the 8th. Again, those are exponents with the same base, so we add the powers. Negative 12 plus 8 is a negative 4. Now we aren't done yet. This is not proper scientific notation. There are 2 digits in front of the decimal point. Now, only one of them is non-zero, but we still only want to get down to 1 digit. We want to get rid of that 0 behind the decimal point. We've got to move the decimal point this way. It'll become 4.088. Now, this number became smaller. The power of 10 has to become larger. So negative 4 plus 1 would be negative 3. So 4.088 times 10 to the negative third. We might have 3.9 times 10 to the 7th times 6.8 times 10 to the negative 15th. So again, we're going to multiply our counts. 3.9 times 6.8, we get 26.52. For our powers of 10, we combine our counts, or our names, sorry. 10 to the 7th times 10 to the negative 15th. 7 plus negative 15 is negative 8. Once again, there's 2 digits in front of that decimal point, so I have to move it over. Give us 2.652. This number got smaller by 1 decimal place. Our power of 10 gets larger by 1. Negative 8 plus 1 is a negative 7. So now division works the same way. We might have something like 5.76 times 10 to the 13th divided by 1.2 times 10 to the 5th. We divide the counts. 1.76 divided by, or sorry, 5.76 divided by 1.2 is going to give us, I believe that is 4.8. Let me double check. Yes, it does, 4.8. Then we also divide the names. 10 to the 13th divided by 10 to the 5th. When we're dividing exponents with like bases, we subtract the powers. 13 minus 5 is 8, so that is 10 to the 8th. Now we can occasionally run into things like this. 3.24 times 10 to the 13th divided by 3.6 times 10 to the 4th. We divide the counts. 3.24 divided by 3.6 gives us 0.9. Then we combine the powers of 10. 10 to the 13th divided by 10 to the 4th. Again, we're dividing exponents with the same base, so we subtract the powers. 13 minus 4 is 9. Now here we notice that this is not proper scientific notation. There is no digit in front of the decimal point except for the 0. So we're going to have to move this decimal point to make that 9. That number got larger, so by one digit, by one place value, so our power of 10 gets smaller by 1. So that becomes 10 to the power of 8. So it's 9 times 10 to the 8th. Division can get kind of wild when we throw in the negative powers. So we might have 7.21 times 10 to the negative 12th divided by, let's see what I want to put in here. 4.05 times 10 to the 8th. So we'll divide the counts. 7.21 divided by the 4.05 gives us, we're going to round that to 1.78. 10 to the negative 12th divided by 10 to the 8th. Remember, when we're dividing exponents with the same base, we subtract powers. Negative 12 minus 8 is a negative 20. We might have, let's see here. 6.76 times 10 to the 5th divided by 5.2 times 10 to the negative 11th. So we do 6.76 divided by 5.2 gives us 1.3. We also then have to divide our names. 10 to the 5th divided by 10 to the negative 11th. Again, we subtract powers. 5 minus a negative 11, written like that, becomes 5 plus 11, or 16. So that is 10 to the 16th. We can go to the next step. We can look at exponents with our scientific notation. So we might have something like 4.8 times 10 to the 7th to the power of 5. Now, just like with algebra, we have to take the count to that power, 4.8 to the power of 5, which is going to give us 2548.04, we're going to call it. And then we do the name as well. 10 to the 7th to the power of 5 is 10 to the, remember we take an exponent to another power, we multiply the powers. So 7 times 5 is 35. Now this again is not proper scientific notation. So we have to move our decimal point. Here we have to go over 1, 2, 3 places to make that 2.548. We'll round it there. Now that number got smaller by 3 place values. Our power of 10 gets larger by 3. 1 for every place value, we move the decimal point. So this is 2.548 times 10 to the 38th. We can even run into something like this, third root or square root or whatever. And we're going to do a third root of, now I'm just going to throw a number in here, 5.21 times 10 to the 18th. So again, we have to split it up. We're going to do the root of the 5.21. So the third root of 5.21, each of your calculator will have a different way of entering this, is 1.73, we'll call it for now. Then we have to do the third root of the power. Now, for when we had a exponent to another power, we multiplied the powers. When we have the root of an exponent, we divide the powers. 18 divided by 3 is going to be 10 to the 6th. That might be a new rule of powers for you. If I have the 5th root of x to the 30th, to take that 5th root of the power, it is 30 divided by the index of that root. So that would be x to the 6th in that case. Now, the scientific notation, like I said, if you go on the medical fields and you have to take chemistry, you're going to deal with moles and other things like that where you have a large number of particles. And you're going to need to represent those particles with scientific notation. Even in physics and electronics, you get into electron volts and things like that that are very, very small. You have to be able to express those in scientific notation and do operations with them. Also, outside of chemistry, but in any scientific field, you end up doing operations with metric prefixes. Now, we haven't talked about this stuff yet, but let's just take a look at a simple electricity example. The voltage in a circuit is equal to the current, which is represented by the letter I, times the resistance. If I have let's do this. Yeah, we'll do 2.5 milliamps as my current, and I have 4.8 kilo, this symbol is actually for ohms, as my resistance. Well, when I put that into my formula here, 2.5 milliamps times 4.8 kilo ohms, doesn't make a lot of sense with those units like that, but those metric prefixes actually represent powers of 10. Now, the metric prefixes don't always come out to be proper scientific notation because they're actually something called engineering notation, where you're allowed to have more than one digit in front of the decimal point. Well, let's take a look at this. 2.5 milliamps. Milli is the exponent 10 to the negative 3. So that is 2.5 times 10 to the negative 3 amps. 4.8 kilo ohms. Kilo is 10 to the positive 3. So 4.8 kilo ohms is actually 4.8 times 10 to the positive 3 ohms. So now we can do 2.5 times 4.8, which is, I believe, 12, but let's take a look. And it is 12. Well, 10 to the third, 10 to the negative third times 10 to the positive third is 10 to the 0, which is just 1. And an amp times an ohm, I wouldn't expect you guys to know this, but that would be a volt. So 10 to the 0 is just 1, so the answer here is just 12 volts. So these powers and dealing with those powers in our operations is important in a lot of different areas. Okay, so for today, we're running out of time. So homework for you guys to work on page 84 of your book, 1 through 31, the odds is converting numbers from scientific to standard notation and back again. Page 87 through 88 is going to deal with, actually the 84 is dealing mostly with dealing with the powers. 87 and 88 is going to deal more with the scientific notation. That'll be 1 through 39, the odd. So next on Friday, we're going to start actually dealing with our measurements and conversions. We'll spend a few days on that. And we are getting close to wrapping up our unit here. We'll talk about it more on Friday. Our next unit test will come maybe not the end of next week, but the beginning of the week after that. So either the end of week 6 or the beginning of week 5 coming up here soon. You guys have a great day, and we'll see you on Friday.